Good morning. We continue our lecture on structural steel, and we have seen in the last class that this is the bulk of steel which is manufactured worldwide. It is primarily addresses, it is primarily used for various structural application, and there is an excellent payoff if we can use or if we can cut down the use of steel. I mean, the best way to use improved quality steel where its strength is higher. So, you need less tonnage. So, that means more efficient use of steel. There has been lot of work has gone in the last 3 decades to develop a range of structural steels which have best combination of strength and toughness. And we looked at the principles behind it, and what we talked about in the last class. If we know, we defined structural steels and how steels are made. I think these are the important stages. We must know about what is kiln steel, and today bulk of steel which is produced by continuous casting route, they are all kiln steel. So, you also have ingot route, you have semi kiln and reaming steels also. We looked at the differences, we talked about steel designations, we talked about strengthening mechanisms, and we found that the mechanisms, most of the mechanisms, I mean, if you try and increase the strength, toughness goes down, the ductility goes down. But for more most of these applications, they demand best combination of strength and toughness, and this is where grain refinement comes out to be quite handy, and most maximum emphasis has been given on grain refinement, and that is the very basis of thermomechanical processing. We shall talk about this thermomechanical processing, how it has helped in producing a range of high strength low alloy steels where alloy content may be extremely small. We will look also a little bit again on the strength toughness, that relationship, and again, and we will all talk about few ultra high strength steel which can be produced by controlling thermomechanical processing. That means, these are, we are not necessarily considering alloy steel. Even in plain carbon steel you can get ultra high strength by controlling this composition and processing. We will see how. And if you recollect your last lecture, we talked about thermomechanical processing. If the working is done above recrystallization temperature, we said it is hot working, and the bulk of the deformation from the continuously cast billet that is done through hot working, and cold working is often done in the finishing stage, and often after cold working the steel may have to be given some amount of annealing to relieve the stresses or to get a recrystallized structure to get a better ductility or best combination of strength and toughness. Now, more technically, if you define that hot working, here you have instant recrystallization on plastic deformation. But this recrystallization, we will talk a little bit about the recrystallization temperature. This recrystallization temperature, it is a it is not a definite fixed temperature. Say, it also depends on a number of factors. It also depends on the amount of working that you put in, amount of stored energy that goes in during plastic deformation. It also depends on the rate at which this deformation is given. It also depends on the amount of deformation. So, it is not a fixed quantity, and here this is if we understand the factors that determine recrystallization temperature, we will be able to design a thermomechanical processing route by which you can get best combination of strength and toughness. Now, this is a schematical diagram which shows rolling. Say, hot working is a process, you can say this is the initial structure, grains here you can say these are equiaxed, and when you deform, the grains start to become elongated, and this reduction in this grain thickness, this is a measure of the amount of reduction, and depending on that amount of reduction, after it job comes out, a recrystallization process can initiate. This is what has been represented here. So, initial bulk of this deformation to steel is given in austenitic state. So, say around the temperature, let us say 1150 around 1150,000 degree centigrade, maybe that is the place where you give this large deformation, and after deformation, either you cool it, if you want to these new grains which form, they will grow with time. And so, the key to get a fine grain structure is to give, and if you recollect here, it will be worthwhile to recollect the relationships which were derived. That means, whenever new stress free grains develop, they depend on certain factors. It depends on the new that interface which is being created, that is the recrystallized austenite and the cold worked austenite. This has a surface energy which is gamma, and this is proportional to that critical size of the nucleus is proportional to this surface energy gamma, and inversely proportional to the amount of energy that is gets stored due to the deformation. Now, this, if you give large amount of deformation, you can see that the activation hill that goes down. If this activation hill this goes down, then the nucleation rate here, you say that this is the nucleation rate. We did talk about these at length in the initial portion of the course, and here if this becomes less, you can see this is a negative sign. So, therefore, this becomes quite large. So, higher cold work means higher is the nucleation rate. So, the key to get a fine grain structure is high amount of deformation. So, per pass try to give as high deformation as possible, and this will have lower recrystallization temperature. So, this recrystallization temperature is also depends on this activation hill. So, you can say that recrystallization, because the nucleation rate becomes quite high. So, this also indirectly affects this recrystallization temperature, and your critical nucleus radius, this decreases, therefore, you have fine grain. So, to get fine grain in finished rolling is done just above the recrystallization temperature, and see that you do not allow time for grains to grow. And here another important thing is, after cold this hot working, the structure does not remain as austenitic. So, it will undergo subsequent transformation, and in fact, what it matters ultimately, factors that determines the ultimate property will be the ferrite grain size. And we will see now, before we go into that, how do you control the ferrite grain size? A quick look at the basic principles of the grain refinement and why it improves strength, yet does not, like all other strengthening mechanism, it improves toughness as well. And so, this is the only mechanism that improves both strength and toughness. Now, any polycrystalline material which is pictorially shown here, it is made up of, so let us consider a single phase material. These are the different polycrystalline, the different crystals which are arranged at random, and we have one picture over here. So, there say suppose this is a coarse grain structure, and now you think about it is made up of two constituent, one is the grain, another is the grain boundary, and it is possible to visualize that strength of each separately, and it has been reported that at a temperature, lower temperature, the grains are stronger, grain boundary is stronger than the grain. So, this is So, this is the line which represents strength of grain as a function of temperature. As temperature increases, strength decreases. This is true for both grain as well as grain boundary, but grain boundary loses strength. This slope is much steeper. So, there is a critical temperature. This temperature is called equi-cohesive temperature. This is the temperature where both grain and grain boundary have same strength. Beyond that, the grain boundary is weaker. So, therefore, what you have in actually you will see that at a normal temperature we will have a transgranular fracture. If fracture occurs, let us look at the sheet here. So, these are the different grains, and so what happens is the strength of any polycrystalline material, this will, you can say this follows, this is the lower bound. So, below this temperature grain boundary is stronger. So, the crack does not pass through the grain boundary, it is the grain through which the crack passes, and you have transgranular fracture. And if there are cleavage plane, imagine say here that crack is taking place, this is the crack, and when it reaches this grain boundary, now for it to propagate you need another cleavage plane over here, and possibly this is the cleavage plane, and which may not be favorably oriented. So, therefore, even if the crack propagates through a grain which is favorably oriented for the cleavage crack to take place, it does not automatically go to this. And at this temperature, therefore, similarly, so these are the paths. So actually this is how the crack is likely to propagate, and so therefore, at every grain boundary the direction has to change, the new grains, the next grain, neighboring grain may not be favorably oriented for the crack to grow. So, therefore, the crack stops. So, this is why you can say that if you have so the strength of a polycrystalline material will be influenced by grain size. Now, fine grain structures, they are stronger at low temperature, which you see here, whereas and in fact and the fracture at higher temperature, it takes place intergranular fracture, because the grain boundaries are weaker. So, therefore, what you try to do, since at lower temperature grain boundaries are stronger, we try to have more grain boundary. So, in the finer grain structures we will have, they will be stronger, which is shown over here. These are the fine grain structure. So, here a crack propagating cleavage crack, only this small distance, after that it meets an obstacle and does not propagate either. So, therefore, there is it has a greater resistance for the crack to grow. So, the grain boundary, they act as crack arrestor. So, therefore, so in this way what we can build upon it is if we make the grains finer, it will have much more or higher resistance for towards crack growth. It will not allow crack to grow, and it will therefore have high impact value, high toughness, and we also know it is particularly important for body centered cubic structure, where you have cleavage plane. So, this is a plane on which crack can propagate easily, and it is also characterized by a ductile to brittle transition temperature. We did talk about it earlier, and if you can make the grain finer, you can lower the ductile to brittle transition temperature significantly. So, therefore, the best way to improve strength without sacrificing strength or ductility is to apply grain is to use the grain refinement technique to improve the strength. Now, let us look at what are the factors that determines the grain size of ferrite, that phase which is present in most structural steel, and this is shown over here. So, there are two important factors. One we have seen is the cooling rate from austenitic state, because ferrite is a low temperature phase in steel. It does not exist at high temperature, or this is not the crystalline structure which exists during hot working. It forms from high temperature phase austenite, and its grain size will depend on the cooling rate from austenitic state. It will also depend on prior austenite grain size. Now, suppose you have one case, you have two samples. One case, the prior austenite grain size is large, which is shown over here. So, this is a large grain size, and another case you have fine grain size. Now, what will happen? We know that new grains, that ferrite grain, when it forms, when you cool below the critical temperature, ferrite grains will form, and the most favored nucleation sites are these. So, ferrite grains form here. So, and most favored sites are these grain edges. So, these edges, these grains will form, and they will try to grow, and with time they will grow. And so, you can clearly see when these grow, ultimately they will impinge, and what you will have, you may get say a grain here, this will be the ferrite grain, another grain going something like this. Now, imagine same thing here. Here the grain size is finer. So, therefore, you have more sites for this ferrite grain to nucleate. They all nucleate at these places, let us say, and again you go through the same exercise. You assume that they are, even if you assume all these grains which have nucleated, they grow at the same rate. In between also you may have some nucleation possible. So, in this particular case, when they grow, obviously you will find, since you have more nucleus, and when they grow and ultimately they impinge, the grain size here is likely to be finer. So, if you have the initial grain size, austenite grain size is fine, the final ferrite grain size is expected to be finer. And then to understand the effect of cooling rate, we should look at the transformation diagram of the steel. Say, let us say this is the transformation diagram of the steel. This is the temperature at which A3 temperature, where during cooling, let us say the ferrite nucleus begins, but here the cooling rate has to be very slow. So, this is the equilibrium temperature at which ferrite nucleus is likely to appear. But in reality, we have seen in the time temperature plot, this is the CCT diagram. We have only plotted that upper relevant portion of the CCT diagram, and this is the line which represents initiation of ferrite precipitation. Now, we have superimposed two cooling rates. One is a relatively slow cooling rate, another is a fast cooling rate. Now, in the fast cooling rate, you know, this transformation takes place at this temperature. So, let us say this temperature, whereas at slower cooling rate, transformation takes place at this temperature. So, what you find over here, the driving force we have seen is this degree of the supercooling, or so this is the temperature undercooling you have over here, whereas here you have, this is the level of undercooling. So, the driving force for nucleation is higher over here. So, what it means, higher the driving force, finer will be the nucleation sites and faster will be the nucleation rate. So, you can imagine, so in these two cases this is the original austenite grains, and here when this has just started, you may think that here you have a very fine grains which have nucleated. Here also let us say at these sites these grains have nucleated, and these fine grains when they grow through a diffusion control process. At higher temperature diffusion rate is faster, and also you can say here in this particular case, since driving force for nucleation is more, this will be finer, where these nucleus, critical nucleus is larger. So, nucleus which forms here, they will be larger to start with, and secondly here you will have more number of nucleus, finer nucleus. So, you may have some grains here. So, when they grow over here, so all of these, large number of these are growing. So, you have, so quickly all these gets filled up, you have more nucleation taking place here. So, ultimately what happens in this particular case, you will get a finer structure. So, that means faster cooling rate, higher cooling rate, that means a lower transformation temperature, therefore, higher driving force. Therefore, the activation hill which has to be overcome for nucleation to take place is lower. So, therefore, and it has obviously it will have higher nucleation rate n dot. So, therefore, we can say by controlling the cooling rate and prior austenite grain size, it is possible to control the grain size of ferrite and the final structure. Now, let us see what impact it is likely to have on the properties, that is ferrite grain size, because ultimately at room temperature you have ferrite is the measured phase, because bulk of the steel percentage carbon will be extremely low, say maybe 0.1, or there are many grades where it is even lower, it could be 0.07, 0.08. These are grades have become quite popular. So, therefore, it will be this microstructure will be mostly ferritic, and here this diagram shows how this strength, the yield strength which is in MPa megapascals, is likely to vary when we vary the grain size, and this axis is 1 over root d. We know we did talk about that Hall-Page equation, where the yield strength is given as, this is you can say lattice friction stress K over root over the grain diameter. So, clearly you see if you plot this against 1 over root d, you expect a straight line. So, this end means it is a coarse grain, this end is fine grain, and around say here this side you have a around micron size, and this size is very coarse, maybe 100 micron, and it can have significant effect. Say that means this increase in strength from here to here is around say 300 megapascal, which is a substantial increase in strength. And we will see, if you check up this solid solution strengthening can never can really approach such a high magnitude of strengthening. Most solid solution strengthening may be of the order of 50, 60 MPa, or depending on the alloy element. And since the grains become finer, it will be more difficult for the crack to propagate. So, therefore, we expect that this ferritic steel will have much higher toughness, and one measure of this toughness is transition temperature. Transition temperature, all particularly ferritic steel suffers from this problem. At low temperature, ferrite is brittle, it has a cleavage plane, that means crack propagate easily on 100 plane, and you get a brittle fracture at a lower temperature. And the temperature at which the fracture becomes brittle, that is known as fracture appearance, or you can say that is the transition temperature. And if you measure this impact transition, and this is the best way to measure is by impact testing. So, ITT means impact transition temperature, and using Charpy that is pre-cracked or Charpy test pieces, you can find out impact transition temperature by conducting a test at various temperature, and here the temperatures are noted here. So, look at it is also possible reported that you can have as low as minus transition temperature as low as minus 150 degree centigrade if you can reduce the grain size to micron level. Whereas, normally if you have a coarse grain structure, this transition temperature at room temperature may be transition temperature may be close to room temperature, and this is quite important, and particularly important if as we will see later, that particularly because these days one of the major fabrication technique for plate and sheet is welding, and when you weld, the problem comes up and you try to see that after welding you do not deteriorate the fracture toughness. So, if you have a fine grain steel and after welding also this should be fine grain, and that is why I think there is a major incentive in lowering the carbon content and maintain a fine grain structure. Now, next we must look at one of the factors that determines the fine ferrite grain size is the prior austenite grain size. And now, let us see how do we control the austenite grain size. So, primarily for all hot working processes, this is done in austenitic state. So, if you have purchased say if these are say billets, continuously cast billet, if they are to be hot rolled, they must be austenitized, and if you austenitize, you have to do this process under a controlled conditions, so that you do not allow the grain to grow abnormally. And how does this abnormal grain growth take place? Now, we know the steel, it has say room temperature, microstructure will be ferrite and pearlite. Ferrite was virtually this is a BCC structure, and pearlite is made up of ferrite and carbide. And when you heat it to a particular temperature, say normally we heat it at a usually most cases say soaking time is fixed, maybe few hours, so 1 hour depending on the size of the stock. It can be from it can even be several hours long depending on the stock size that you have. And when you heat it, say suppose you are heating it at this temperature, you will initially and this austenizing temperature is definitely a function of time as well. So, suppose if we fix up the time, see first when it crosses that lower critical temperature, this pearlite disappears, it forms austenite in the pearlitic region, but some carbide may remain undissolved. So, you will have a region where you will have ferrite, austenite and carbide. As you increase the temperature, amount of ferrite goes on decreasing, and over here you will have all ferrite, this is the line which represents the conditions, the time temperature condition where ferrite disappears. And here you have austenite, but still you may still have some of these carbides may not have dissolved in austenite. So, you have a region where you have austenite plus carbide. Now, there is a temperature here where these carbides also dissolve. When these carbides dissolve, there is nothing to pin these grain boundaries. So, therefore, once you exceed this temperature, the grain starts growing at a very faster rate. Now, it is also possible to do some experiment and find out by giving heat treatment, that means heat to different temperature and quench, and then heat to austenizing temperature, say suppose you have heated here and quench. And then what will happen? So, here these are the austenite grains. So, if you quench, all these will convert into martensite here. Say depending on the carbon content, the type of martensite, it can be lath martensite or it can be a plate martensite, because mostly we are talking about low carbon steel where you will have lath kind of martensite. So, you have this kind of martensitic structure formed, and which clearly reveal that austenite, prior austenite grain size. And it is possible to determine this prior austenite grain size as a function of temperature, which is shown over here. Now, this is the temperature. Now, let us say and here you will find, as long as you have carbides which can block the movement or which has pinned the grain boundaries, there is austenite grains do not grow, that growth is slow. But once these carbides dissolve, then the growth increases significantly. So, you can see here. So, this is the critical temperature when all carbides dissolve, you have homogeneous austenite, and you are likely to have under such condition excessive grain growth. So, to get fine austenite grain, one important condition is to see that you do not have very coarse austenite grain in the structure. And how do you do it? And this is what we will cover in the next few slides. Now, how do you control this austenite grain size control during hot working? Now, this is where you make some micro alloy additions. Say normal, if it is iron carbide, it dissolves at a quite a low temperature. So, therefore, this iron carbide or cementite is not very effective in controlling or in suppressing the growth of austenitic grain. And we try to add certain very strong carbide or nitride formers, which are much more efficient in blocking or in pinning grain boundaries. And these alloy additions are called micro alloy additions. They are called micro alloy because total alloy additions may not exceed 0.2%. And these micro alloy additions form precipitates, particularly it is nitride, carbides, oxides, and they block the movement of austenite grain. So, this is one important. Second is you control the recrystallization, that means thermomechanical processing, you control in such a manner that you are able to control the recrystallization of austenite during hot working. Now, these microalloy addition we talked about, these are the common additions. We did mention that when you add that aluminum keel steels, you have likely to have fine alumina, and usually aluminum keel steel, they are inherently fine grain structure. Now, each of these elements, they have very high affinity for both carbon, nitrogen and as well as oxygen also. So, to get this, they must be and these are very intentionally added element. This niobium pins the grain boundary very effectively. So, also titanium nitride, niobium nitride, vanadium nitride, they block this grain boundary movements. So, and if you want to use these to the maximum, we must ensure that steel should not have too much of oxygen. So, aluminum is primarily added as a deoxidizer to control oxygen and balance that carbon and nitrogen whatever is there in the steel, they form nitrides or carbides with these microalloy additions. And criteria for selection of this is all these should be present as dispersoid, and this is possible only when each of them they have very low solubility. So, that means solubility of each of these vanadium, titanium, niobium should be low in steel and should have high affinity for these elements. And the reaction that takes place, which is written over here, if when you add niobium to the steel, it reacts during steel making, it will react with nitrogen and it can form niobium nitride. Now, it is quite important to know at what temperature these niobium nitride will form, and can we control this formation of this niobium nitride during hot working. Not only niobium, there may be other alloy elements, 1 or 2, vanadium, titanium. So, each of these carbonitrides, how can you control their formation during hot working is the key to the thermomechanical processing. Now, we talked about, let us talk about the solubility product. We said that these are soluble in steel in a very low amount. So, niobium which is dissolved in steel, then nitrogen which is dissolved in steel, and the solubility product is the weight percentage niobium in steel, weight percentage nitrogen in steel, which remain in equilibrium at a particular temperature. So, this is a strong function of temperature, and it is quite it is possible to show very easily. Here we will see here. So, if you consider for any chemical reaction like this, you have soluble niobium in steel, soluble nitrogen in steel in solid state, you see, and they are forming, they are in equilibrium with niobium nitride. So, this is the equilibrium constant, and these are, you can say, that activity of these respective phases. So, this is dissolved niobium, dissolved nitrogen, and this is the niobium precipitate. We can assume that this activity to be 1, and these are, since they are present in very small amount, we can say that their activity is proportional to weight fractions of this respective element, that is weight fraction niobium, weight fraction nitrogen. And this we know that this activation this equilibrium constant is related to standard free energy for this particular reactions, and with this it is possible to show that log of this solubility product will be proportional to this. So, that means if you plot logarithmic of this solubility product, it has this kind of a plot. T is a temperature in degree Kelvin. So, this is a strong function of temperature, and it is quite important and to see that how this solubility product changes with temperature, and periodically it is typically it is shown over here. If you assume that this is the solubility product at a particular temperature, it is constant, then this represents a hyperbola. So, which is shown over here, this is the solubility line, you can say. So, that means if you have this much of soluble niobium, this will be in equilibrium with this much of nitrogen. So, what you can see, if you have a small amount of niobium, this is the amount of niobium, then amount of nitrogen in the steel can be high. So, similarly, if you have high amount of niobium, amount of nitrogen in steel is very low. So, you have to maintain an optimum quantity of soluble nitrogen or niobium in steel, so that you get optimum amount of this dispersoid. And how do you get it? Now, for this it will be interesting to look at effect of temperature on this solubility line. If you increase the temperature, higher is the solubility, say this is the line. And if in a steel you have this much amount of niobium, this much amount of nitrogen. So, if you are heating here, then all of these goes in solution. So, if you go beyond, so you can say this is the critical temperature roughly. So, if you are austenizing beyond this temperature, the austenite will grow. So, if you grow close to this, where some amount of niobium nitride is still there to the pin the boundary, the grains will not grow significantly. And next is, as you cool, the temperature will go down, say from T1 it will come down to this. So, you will have more and more amount of niobium nitrides precipitating out, and it is possible to calculate that amount from this type of diagram. And what you need to know the stoichiometry. If it is 1:1, in that case you can plot that stoichiometry line something like this. So, you can draw this similar parallel line from here, and from this it is possible to find out amount of vanadium and amount of amount of this niobium nitride, which will form at various temperature, and it is essentially be a function of temperature. Now, next let us see what is the nature of the solubility product plots. So, which is shown over here, and we have seen the lower solubility products, the better or more effective is the dispersoid. If you look at the solubility product, you find these nitrides, they are much more effective because their solubility is less. Relatively carbides, these are approximate composition, you can say this need not be exactly VC, it could be some numbers here. So, but nevertheless what it means, these carbides and carbonitrides, these plots, this solubility product plots, they are linear when plotted as against 1 over temperature, and nitrides are much more effective as dispersoid. These nitrides are more effective as destroyed than carbide. Now, the question comes, how do we schedule our hot rolling, and this here it is pictorially shown here. This is the time temperature plot, and let us say these are the temperature at which ferrite formation is possible, and this is the temperature at which pearlite may form in the steel. So, these are the equilibrium temperature. Now, suppose we are giving reduction to a stock, and this dotted line, this represents the mean stock temperature, and initially this stock size, this length, this represents the initial stock size, this part, and here you are gradually the stock size, this thickness is decreasing. So, this is the temperature range where you give the initial rolling. And here it is also shown here, these are the critical temperature above which you have homogeneous austenite. So, if you have homogeneous austenite, these grains may have grown. So, typically which is shown here, Above this temperature you have this coarse austenite grain, and when you are giving reduction you try to give as high reduction as possible, and higher temperature the strength of the material is also low. So, therefore, you can give high reduction, and if you give high reduction there may be rapid recrystallization also taking place here, and because of this these grains they deform and fresh they are replaced, they get deformed and they get replaced by new strain free recrystallized grains. And after that there is a delay, you do not give any work. So, here this much reduction has been given initially, and after that since you are not giving any reduction, these grains strain free grains they can grow also. So, this is how it has grown, and this is a temperature where we say that we try to give over here another rolling, that is the final rolling, and so here again you see this thickness size is decreasing, and if you give the final rolling here. So, there is a stage here, these austenite grains which are this size they get elongated like this, and here it is only that since you are giving a very large reduction, now the temperature also is substantially lower. So, we know that recrystallization rate also will be low. So, here if at all recrystallization is taking place, there will be very few recrystallized austenite grains. Bulk of it still remains elongated, and if you even continue this even further, it is also possible, if you give even higher reduction, it is also possible to not to allow any nucleation to take place, any strain free grain, that means no recrystallization is also possible, and by that time your work is over and you allow it to cool, and that is the time the grains which form, these are fine, these are the grains which will form the ferrite grains which will nucleate, and it will nucleate particularly even because this grain austenite grain which has been cold rolled, here it is very thin and it has very large surface area where grains can nucleate. So, therefore, you have large number of these ferrite grains forming. So, if you have ferrite grains nucleating in such thin thin grains of austenite, the final ferritic grain size is expected to be extremely fine. So, this is the principle of controlled rolling. You roll in such a way, you control the temperature, control the cooling rate, and so that here you can delay, but you may be able to cool it little faster or something, so that even this grain growth can be stopped. And finally, this is the stage when the ferrite grains have nucleated, and later on we will see that you can even control how it is actually done in a rolling mill. So, which is schematically shown over here, this finish rolling which is done over here, and this finish rolling temperature is substantially low. It is maybe depending on that carbon concentration, it could be around 850 to 900 degree centigrade. You finish the rolling, and after that here this rolling is over, and then you cool it little rapidly. So, that if you cool it little rapidly, this temperature cooling it rapidly, and then here the ferrite which starts forming forms at a much lower temperature. If your so, this is the degree of supercooling, and higher the supercooling, finer will be the ferrite grain, and here the ferrite grain formation is nearly complete, and this is where you take it out, and here you coil it, and it is rolled into a coil, and when it becomes a coil, obviously its cooling rate will be slow, and the coiling temperature is around when that ferrite formation is nearly complete, that is the coiling temperature. So, this is how actually it is implemented in practice in steel plants. And then factors, let us look at the factors that determine final that recrystallized austenite grain size. It depends on several factors, it depends on the temperature, strain rate and strain, and which is shown here. So, that means during hot working itself, and you will be finishing the working see around let us say 900 degrees centigrade, and that is the time, if you finish here, you are likely to get a fine grain structure. And strain per pass, higher the strain you give per pass, finer is the grain. Higher the strain rate, finer is the grain. But there is a major limitation of this controlled rolling process. Now, one is the controlled rolling. If you roll at a relatively low temperature, that means here controlled rolling, you roll below austenite recrystallization temperature. Do not allow the recrystallization to take place, so that you have this kind of a pancake type of structure. So, here you have obviously, if you do not allow this to recrystallize, it will have a high strength, you need high rolling load. So, ferrite nucleation, you do get extremely fine ferrite grains, because it nucleates in pancaked austenite, because these are very thin, it has very large number of sites for nucleation of ferrite grains. So, this is a major problem. So, by controlling the working, so you can also possible by controlling recrystallization control rolling, where you allow these nitrides to form during recrystallization and inhibit the new recrystallized grains, do not allow them to grow. So, this is where this is the initial, you roll and then it is recrystallizing, and that is the time, if these precipitates form, they will form here and they will block, they will not allow these grains to grow. So, that you have fine recrystallized austenite, and here your rolling load is low, your finish temperature is little high, you finishing the rolling temperature is in the temperature zone where you have these precipitation taking place. Now, a quick look at this, we looked at by thermomechanical processing, by controlling the transformations, how we can get extremely fine grain structures, and which have very good strength and toughness, and as we will see later, they also have very good weldability. Another important class of steel where you get good combination of strength and ductility is a dual phase steel. Now, what happens? See, in normally these steels we process, we give what we do, we cool from that intercritical region, we give an intercritical heat treatment to steels. Say suppose it is also possible to do it online also. Say suppose if you quench a steel from somewhere here, this temperature. So, what do you have here? You will have ferrite and austenite, ferrite plus austenite. Now, here if you quench, so over here, so you will have these are these austenite grain, and these are let us say ferrite grains, and these are let us say these austenite grains. And here if you quench, it is possible that room temperature it has a ferrite perlite structure, but if you come over here you get ferrite plus austenite. From here if you quench, ultimately it is possible to get ferrite plus martensite structure. So, here and this martensite will have a relatively higher carbon content, and this method is being exploited. This is a potential method which can be exploited to develop a steel which has good combination of strength and ductility. And so, maybe I think to understand this, I think we have to spend a little more time. Maybe we will talk about it in the next class. So, today what we have looked at primarily is looked at thermomechanical processing and how by adding microalloy addition it is possible to retain very fine austenite grain size in which fine ferrite grains can develop. We looked at effect of temperature, strain and strain rate on that austenite grain size. We talked about controlled rolling, that means rolling at a lower temperature, but this has some problem, whereas recrystallization controlled rolling has become more popular, because here rolling is done at a little higher temperature where steel is still soft. So, rolling load is less, and by this technique it is possible to get extremely fine grained ferritic steel primarily, and it will have some pearlite no doubt, but it will have definitely best combination of strength and toughness. And we also introduce the dual phase steel. I think these three we could not cover. I think before we proceed, we will cover this in the next class. Thank you so much.